room.
Okay, let's do it. We're going to start doing some algebra, some setting up of problems. The algebra comes last. You know, it's not about the algebra, that's part of it. We need to set it up. We're going to do basic energy accounting. If you keep hold of this as you go on to things like electricity, magnetism, a variety of things, you'll still have this basic idea and you'll be able to write equations that make sense and are tailored to your problem. So do it. Here's the basic idea. So energy accounting. Again, we're going to derive the full thing after we do this introduction. It's very important to kind of see the structure. This is how we work, really. This is how we set it up. The general idea is that interactions with other objects will cause a change in the object or objects of interest, right? And that's true for net forces cause a mass to accelerate, right? The acceleration being the rate at which it changes. Impulse causes a change in momentum. And so we'll talk about this again more later. We'll introduce work later. So for now, any energy that's added from other objects minus any energy, absolute value, so I'm taking that as a positive number, taken away from other objects, causes our object or objects of interest to change their energy in whatever form. That's the basic idea. It's just accounting. What goes in minus what goes out equals what you changed, right? But these are interactions. I'm going to stay strong with that. Or you could write these two here. You could say, well, let's just call this energy from others. So energy added or taken by others, right? So added would be positive and taken would be negative. So however you account for that, right? And what does that do? That causes a change in energy of the objects of interest. What's the energy? Well, you're going to go from a later state to an earlier state. That is a later state minus an earlier state. So however much energy we have, all the kind of energy that our objects have earlier, and then we look at how much it has later. So the later minus the earlier is the change, is what I'm trying to say. Okay. The notation's a little funny. I know I use later and earlier. A lot of books don't yet. E can mean energy here, and it can mean earlier. But you know, M can mean mass, and it can mean milli, and it can mean various things. So we're just going with it, right? It could mean meters. So earlier works well. So you can have state 1 and state 2, or state 1 and 3, or 2 and 4, or 2 and 3, whatever it is. Now this energy is between those states. So from earlier to later, there's some interaction. If this is 0, then we have what's called conservation of energy for our objects. In the larger sense, we think energy in general is conserved. It's always going somewhere. Remembering that energy isn't really an entity, right? It's a property. But we can keep track of it. So there's accounting. That's why I made such a big deal. It's not like energy is money, but we can think of it like money, right? Okay. So here's an energy accounting. All right, various types. So that's general, and we can talk about thermal energies, and we can talk about the energy of light and various things in this way. We're going to start off a little easier and more clearly. Over here, we're going to talk about energy analysis, energy accounting, and the method's going to be like this. We're going to work backwards in our structure. So the first thing we're going to do is look at, choose our object or objects, if say it's a collision of a couple objects, whatever it is. Sketch it, look at it, decide on the earlier state. What's the moment that you're looking at earlier? And what kind of energy is there? So just look at it. Boom. What kind of, do I have kinetic, potential gravity, potential spring? What kind of energy? Those are going to be our main things. And then in my picture, I should have shown a later state. So just look at that. What do you got? What kind of energy at that instant? Maybe you know how much. Maybe you don't know how much, but you know equations. You know what type of energy. Just write it. You're going to solve later. So don't worry about not knowing everything, right? Just setting up the algebra. Set up the equation. Do the algebra solve. First, energy earlier. What have you got? Second, energy later. What have you got? Third, look between the earlier and later states. Are there any interactions that are causing or adding energy, taking energy away? Anything outside of our system of objects, right? How much? What kind of interactions? We'll get into that again later. And then just solve. So you set it up. Now for now we're going to do something called mechanical energy, which is like the bulk motion of things. right? The bulk motion, movement like this. I'm not worrying about the microscopic jiggling and the me glowing infrared, okay? And for that we talk about E mechanical. Mechanical energy is often defined as the kinetic energy, all types, right? It could be translational, it could be rotational. For now we're not going to do the rotation yet, but it'll go right in here. It's beautiful. Just go in with everything else. All the energy goes together. It's one big soup. Plus any potential energies, all types. Okay? So potential energy of gravity, potential energy of spring will be our main players. We get the electric force in another course, and we'll talk about that. So how do I do it? Well, then my equation becomes easy. It's the energy changes from any interactions, causes, so the energy added or taken is what's going to cause the change, the energy later minus the energy earlier. Again, I look earlier, what have I got? Later, what have I got? Between, what happened? Set it up, you'll be given enough information to solve the puzzle, and you're good. Remember that energy earlier, more specifically, is the kinetic. What's a kinetic energy? What potential energy is there? Then later, all you got to look for is kinetic energy, potential energy of gravity, potential energy of spring. If there's no spring anymore, fine. Maybe there was a spring compressed here, and maybe it's gone. It's not in the game anymore. So fine. If this is 0, so the beauty of writing it this way, and I highly recommend writing it this way, if this is 0, then that's conservation of mechanical energy. Of course that means that E later equals E earlier, but why write it as a separate equation? Why not just write one equation and always check 1, 2, 3. If that's 0, justify it, and fine, you've got conservation of mechanical energy. So that's our energy accounting game. All right, now I'm going to just show you this because you might see it rearranged many ways. And early in my teaching, I thought and tried different ways of writing it and was thinking about how it's best to communicate this. I strongly think that interactions causing change is a structure that is very fundamental to physics. And so we could rearrange this. Some people, for instance, will write any energy added or taken away plus whatever I started with, we'll end up with, that'll be what I end up with. And that makes sense too. Right? I can rearrange that. I can say, hey, any energy added plus the energy I started with, all types, is equal to the energy later plus any energy that went out. Right? So I could say, oh, 10 joules was added. I started with, 3 joules was added. 10 joules I had. I ended up with 12 joules, but I lost 1. 13 equals 13, fine. You can also write this, energy added or lost. So 3 was added, 1 was lost, so there's the negative sign. I started with 10 joules, I ended with 12. So it still works, right? 3 minus, that's 2, and that's positive 2 as well. So fine, it works. Again, I highly recommend using this because it's the interactions. And also when you draw your picture, you can say, okay, what's happening first, earlier? Now it's happening later. Now it's happening between those 2 times. So let's try that out. And I'm sure if your text uses something different, I still think this is going to help avoid problems that I've seen very frequently. So for example, let's throw an object upward. Projectiles. Let's imagine throwing something upward. Now you could start your process, your earlier state, anytime you want. So you have to read a problem carefully. Are they talking about right after you release? Or are they actually talking about the throwing process? So let's include it all and just take a peek. Right. I'm going to take an object. Let's get this general form out of here. Looking at the mechanical motion, the kinetic energy, potential energy of gravity, potential energy of spring. I'm going to take an object and I'm going to throw it. So I'm going to go from here and here. All right. And I don't know. You're going to have to define each because I know that I'm going to call this state 1. And here I'm throwing. And here I release. So I'll call that state 2. And then it's going to go up, I don't know, state 3. And then it goes to the top, state 4, you know, whatever is described in the problem. So I'm just putting a whole bunch in here to see how this works. And then it comes back down. I'll make it the same height over here. State 5. State 6. State 7, and so on. All right, cool. Now let's put in some information. So I need to look at my object, and I need to look at the process. All right, so let's see what I know. Just in general, looking at this. Let's talk about velocities. What do I know about V1? I know at that moment I got V1, it's going to start from rest when I start to throw it. And of course that means that K1 is 0, right? Kinetic energy, state 1 is 0. And potential energy is how much? I don't know. It doesn't really mean anything except relative to some place. Now, I'm going to call this H equal to 0, right? If I do that, and again, you can call up here H equals 0, then I'm going to say H1 is equal to 0, set by choice, and so then potential energy of gravity, lowercase g, uppercase g, people use different things. There's no spring in here, so I'm just going to use U, is equal, 1 is 0. There's not a spring, don't worry about it, obviously. Okay, there I go. So fine. And then I go over here to state 2. I'm using another color for state 2. State 2, I know I'm moving, right? That's why I threw it. So I got some V2. I don't know what it is. And then I've got some H2. Speed giving me energy of motion, height giving me potential energy of gravity, right? There. And then from there to there, I've got this, and I've got some, I don't know, V3 and H3. I don't know, I'm not going to solve for anything. We're going to do this kind of a quick setup. We're just doing the accounting. And at the top, do I know anything? Ah, yeah, I sure do, right? I know that V4 is equal to 0. Now hold on, because I'm going to show you something else that's going to be interesting. And that, of course, means in terms of energy, K4 is 0. And H4 is, I don't know. And, of course, potential energy 4 is mgh4, and you can do the mgh for all these guys. And then I go back down here, and I'm going to go, hey, wait a minute, this one was going up, but slower, so I'm going to draw this one longer, and this one a little shorter. And then I'm going to draw, oh, wait a minute. We know this from kinematics, right? This is going to be the same speed. V5 is equal to V3, opposite direction, but in terms of energy, that means K5 equals K3. I've got the same kinetic energy, don't I? If I've got the same speed, not direction. So again, not a vector. And then whatever, H5 is equal to H3, so potential energy at 5 equals potential energy at 3. And I don't know, I'm just writing down things I know. And then 6 is coming on down here. Now you released it here, so this will be the same speed, right? So V6 equals V2, and K6 equals K2, and I've got H6, etc. And down here, this is interesting, is V7 the same as V1? No, it's not going to stop unless it hits something, right? So in fact, it's going to go faster. So I got a V7, and that gives me a K7, is 1/2 mv squared, and I got H7 now, that's equal to 0, right? So that gives me that U7 is 0 by choice. And those are the things that I know at each of those states. Now I wouldn't do, this is kind of overkill, right, in a problem, but you can relate any earlier state to any later state. Now here's the interesting thing too. Suppose I go 1 to 2. Now I'm going to use my basic format. Energy changes between states will equal the energy later minus the energy earlier. So let's do this. Let's go over here, and let me just go 1 to 2. So I really recommend writing that, and then I go from 1 to 2. I'll just say change in energies from 1 to 2 through interactions causes my energy at 2 minus energy at 1. So I go at 1. At 1 I've got 0. because I set that to be 0 at height. That's totally fine. So I got no speed and no height by choice. And then energy at 2. Well, I've got something. I've got 1/2 mv2 squared. And then I've got plus mgh2 minus 0. And is that 0? And no, because I was throwing it. So that's energy added by John. Right? Clearly I gave it energy. This is positive. This we can see is above my 0 point, so that's positive. And so that's going to be a positive number, and it all works. And whatever you work with, you get it. Now let's go take any other time. Let's go from, doesn't matter, from 2 to 3. So let's go from state 2 to state 3. What do? Well, any changes from 2 to 3 is the energy at 3 minus energy at 2. See how quickly you can start doing this and set this up? So what am I going to do? I'm going to go work backwards. I'm going to go energy at 2. What have I got here? Energy at 2, I've got what kind? Well, according to, I could have called that h equals 0. It doesn't matter. You can't overprocess that, right? So here we go. Just get over here. Energy at 2 quickly. See how fast we can do this. Energy at 2. Well, let's see. I've got 1/2 v2 squared plus mg h2. And then my energy at 3. 1/2 mv3 squared. And that's not, I don't have any zeros here, right? Plus mg h3, right? And then what about between the states from 2 to 3? Well, if there's drag, then yeah, you'd be losing some energy, and you'd be slowing down more than just due to gravity. Now, all the while, gravity is affecting this, right? The force of gravity is there. And again, we'll get to that later, but now just account for it. You physics teachers are probably cringing. We're going to get to that proof, but this is how we efficiently think about it, and will motivate how beautiful it is to think of it this way. So from here to here, neglecting air resistance, that's 0. We call that what? Conservation of mechanical energy. Fine. And then we just solve for whatever we need to. Notice in this case, the m's are a common factor. But if there's something over here, you cannot factor that out, right? It's got to be common to all terms. And then you can just work your algebraic magic all you can. Now, what I think is a nice one would be 3 to 4 or 2 to 4. Let's try 3 to 4. I don't know, let's do 2 to 4. That doesn't matter, I just want to make that point. 2 to 4. Well, okay, so I got the changes in energy from 2 to 4 equals E4 minus E2. See how fast you can get? So what kind of energy? Work backwards, work backwards. E2, I got the 1/2 mv2 squared plus mgh2. And E4, I got, oh, look at that's nice, that's nice. I don't have any kinetic energy, do I? So I just got mgh4. And this guy, I can see there's no interactions other than gravity, which is accounted for there. So that's 0. M's go away, easy to solve. Right? Algebra is easy. Setting it up is the key. Hey, what about 3 to 5? I like 3 to 5. Let's check 3 to 5. As fast as we can. How are we doing? Hanging in there? 3 to 5, 3 to 5, 3 to 5. Can you do it? Pause and do it. Pause and do it. 3 to 5. 3 to 5. Cool. I got the change in energy from any externals from 3 to 5 is equal to energy at 5 minus energy at 3. Cool. I'm going to work backwards. Energy at 3, what do I got? I got 1/2 mv3 squared plus mgh3. That's it. Right? Energy at 5, what do I got? 1/2 mv5 squared. That's not 0, so I got that mgh5. Cool. Between the states. It's neglecting air resistance. Fine. Just set it up first. Don't look too far ahead. The m's do cancel. All right, they go away because there's nothing over here. So I do have these constants. If I have a spring, 1/2 kx squared, you can't get rid of the m. You can't get rid of the m. But the m is here, so keep your algebra straight. Wait a minute. V3 and V5, they're opposite direction but the same speed. So these are the same. And H3 and H5 are the same. I didn't even need this. This is a complete waste of time. I knew V3 equals V5, so I know K3. I know all this stuff. So interesting. It works. It works. It's fine. What a waste. Oh well. Live and learn. I can go 3 to 6, right? I can go 3 to 7. And here's the beauty. Notice that you could have done this before with kinematics. Now, you could have done all this stuff with kinematics. When you're learning energy, it's very powerful. So even though you're doing a problem that's simple enough to do with kinematics, work the energy angle, because energy is a tool that analyzes things that get much too complicated to deal with force and kinematics. Okay? So notice it's a very beautiful method here. And you can really quickly get to the exact same answer that you can with kinematics in this case. Now let's try another case. What about this? What if you toss an object and it's flying through the air in 2D? So in 2D, we've got an object, and you can toss it sideways, you could toss it downward, right? You can toss it up. Those are different cases, right? Let's toss it up, whatever. And here, let's say that's state 1, and let's say the top is state 2. All right, so let's see, I got V1. Now, this is interesting. All right. V1, cool. Let's go over here. Energy analysis on this guy. Energy is great. It's not a vector, right? So I've got V1. Now, that's the speed. All right. And then let's look at V2. So let's go from 1 to 2 here. And then the other spot that I like looking at is 3, where H3 is equal to H1. And I'm going to call H, let's see, should I do something crazy? Yeah, let's call this H2, set that equal to 0. Fine. Does it matter? It really, it's not going to matter. The algebra is going to work out, the answer is going to be fine, and it'll have meaning relative to that place. Fine. And then I can go down here just before it lands in state 4 here. So state there. What can I do? Let's do 1 to 2. Highly recommend doing that. Highly recommend just doing this to start you off. E2 minus E1. Fine. What have you got at state 1? I've got 1/2 mv1 squared plus mgh1, which we know is how much? Well, it is where, I should say? It's a negative number. It's whatever that is, however high it went. Okay, and then I've got a minus here, and the energy at state 2. Well, what's the energy at state 2? Well, it stops, so I've got B2 is 0, right? No. It only stops vertically, right? Horizontally just keeps on coasting. So V2 is equal to Vx, which is always the same. So I've got some 1/2 mv2 squared plus mgh2, which I defined to be 0. Otherwise, you keep that and maybe you define this to be 0. Again, doesn't matter. So there you've set it up. Now here's an interesting thing. Well, first off, notice that between the states, I got nothing, right? Cool. This is kind of fun. 0 is equal to 1/2 m, whoop, hello. I could get rid of the m's, let's leave them there for a second. Squared minus 1/2 mv1 squared plus mgh1. Now I can play with some algebra. How are we doing? Good. Cool. So that's kind of fun. What's this algebra? That's equal to 1/2 m. Hey, v2 squared. That's the speed, right? And it's all going in the x direction. So, but I could do v2x squared plus v2y squared. At the top, there's no vertical velocity at that instant, right? It's still changing. This is just something you can do. This is an added little trick for doing the analysis. Initially, or the earlier state, I got v1x squared plus v1y squared plus mgh1. So notice that this, here's a mistake. Don't do this. This is not, now this is true. But don't put that times I hat and times j hat, because energy is a scalar, so it doesn't matter. You've got some from the x motion, some from the y motion, but it's a scalar, so you get to add it up. You don't need to create columns with your unit vectors, directional vectors they should be called, really. Right? So whatever. That's just something you should know. That's not energy analysis. That's basic looking at the analysis. But you know, you do a bunch of problems to pick up on these little subtleties, and that's pretty cool too. Okay, let's try one more. All right. So projectiles on ice, they're often here unless you're throwing it. Then we've